In this video, we are going to overview the new 505XT dual redundant or 505DR, which is the latest release in the 505 product line. The 505DR allows two 505XT units to be applied together in a redundant configuration in order to increase overall system reliability and availability. In order to overview the system, we will be using video clips of the two units. We will show how they communicate and process I/O in order to provide redundancy. We'll go through a boot up sequence. We will configure the units. We'll operate the units. And then we'll go through some fault modes and transfer cases to show how redundancy is accomplished. In a DR system, one unit functions as the system controller, or syscon, and controls all aspects of the turbine system. The other unit functions as a backup and is continuously kept in sync with the syscon in order that it can smoothly take over control in the event of a failure. The syscon and backup units communicate to each other via a direct connect Ethernet link. This link provides the data path for the syscon to keep the backup unit in sync. The units also communicate to each other via a hardwired DO to DI health crisscross link. This provides the mechanism for transferring control. I/O between the two units is shared. The optional FTM provides a single termination point for field I/O. The provided cable harnesses route the field I/O to each unit. Each input channel is sensed and monitored by both units, but only the syscon commands output signals. The syscon communicates control states to the backup via the Ethernet link. The backup monitors input and output signals for health and communicates channel status back to the syscon via the Ethernet link. When power is first applied to the units, the I/O lock LED will come on and indicate that power has been received. The operating system will initialize and then begin the gap control and graphical user interface applications. The units will verify that they can successfully communicate over the Ethernet and hardwired crisscross links. Once the I/O lock LED is off and the CPU LED is on, the units are synchronized and ready to run the system as a redundant pair. When configuration, service, or runtime settings are adjusted in either the syscon or backup, the two units will automatically synchronize the settings so that both units contain identical settings. When a save settings command is issued, both units will save settings to non-volatile memory. It is only necessary to configure or make settings updates on one of the units. The operating system will automatically update both systems to keep them in sync. The front panel HMI interface screens operate independently of each other, providing redundant HMI screens. Next, let's perform a simple configuration of the units. After logging into the configure user level, the units can be placed into configuration mode. Issuing a command to enter configuration mode can be made from either unit, and both units will enter I/O lock. In this example, we will show the same configuration menu on both units. As you can see, making a settings update in one unit automatically updates into the other unit, and making a settings update in the other unit automatically updates back into the first unit. In this way, the units can be configured from either screen. In this example, we will set up an idle rated start sequence. Because the screens are redundant, it can be useful to show different screens on each unit. In this case, it is useful to show the configuration errors on one unit while completing the configuration on the other unit. As the conditions that cause the errors are no longer met, the configuration errors will clear off the list. Next, let's configure an analog input as a remote speed set point to show how I/O is configured. First, we will enable the remote speed set point setting, and then navigate to our channel pages to configure the input. Similar to the other configuration settings, when the analog input channel is configured for a particular function, it is configured as that function in both units. This is because I/O is shared between the syscon and the backup. The analog input for remote speed set point comes into the FTM and then is shared between both units such that they see the same signal simultaneously. In this way, the analog input is configured identically on both units. The configuration is now complete, and we can exit configuration mode in order to show operation. Now that the units are in operation mode with a completed configuration, the DR overview page is available from the home screen. The DR overview page provides diagnostic information of the redundant system. This screen will indicate which of the units is currently operating as the syscon and which unit is the backup. If the backup unit is unavailable, this screen will indicate the fault that needs to be repaired in order to restore system redundancy. The LEDs on the front panel also indicate which unit is syscon and which is the backup, and if the backup unit is healthy. A solid green CPU LED indicates that that unit is currently the syscon. A flashing green CPU LED indicates that that unit is currently the backup, and that it is available for a syscon transfer, meaning that the backup unit is healthy. A flashing amber CPU LED indicates that that unit is currently the backup, but that it is unavailable for a syscon transfer due to a fault condition. Next, let's start the unit. Trip conditions can be cleared by pressing the reset from either unit. Once the trip conditions are cleared, a start command can be issued from either unit. All commands via communication links, whether it's the front panel graphical user interface, remote view, or Modbus, can be issued to either the syscon or the backup unit. The operating system will ensure that the commands are processed by the syscon unit and that the control state is passed to the backup unit to keep it in sync and available for a transfer. The syscon controller will operate indefinitely as the syscon unit. A transfer of control is initiated if the syscon 505 fails due to a CPU or other internal problem, there is a loss of power to the syscon unit, there is a loss of all speed probes to the syscon, the actuator output on the syscon fails, there is a CAN communication fault, there is an analog input sensor failure on the syscon, there is a readout analog output failure on the syscon, or there is a manual user command to transfer unit. Next, let's demonstrate a user transfer of the syscon control. In this video, the top unit is currently the syscon controller, indicated by the solid green CPU LED, and the bottom unit is currently operating as the backup unit, indicated by the flashing green CPU LED. When the command for a user transfer is given, the syscon will become the backup, and the backup will become the syscon, and the LED states will have changed. Here, the new syscon took over control of the turbine smoothly, as indicated by the speed trend. Next, let's demonstrate what happens when the syscon unit loses power. In this video, the bottom unit is currently operating as the syscon, and the top unit is operating as the backup. When the syscon loses power, the backup unit becomes the syscon and takes over control of the turbine. The new syscon unit will continue to operate the turbine until the backup unit is brought back online. If the backup unit has failed and needs to be replaced, it can be done while the other unit continues to operate the turbine. The replacement unit can be connected back to all of the I/O and communication wiring before applying power. It is not necessary to configure a replacement unit prior to bringing it online. Once the syscon detects the backup unit, it will update the backup unit with the current control state of the system, including all configuration and service settings. Here we have applied power to the backup and are waiting for it to synchronize back into the syscon unit. Now that the backup is synchronized, we can see that it is unavailable and a reset must be given to restore system redundancy. Next, let's demonstrate what happens on an actuator failure on the syscon unit. The top unit is currently operating as the syscon, and the bottom unit is currently operating as the backup. Here, an actuator circuit failure on the syscon will initiate a transfer of control, and the fault will end up being enunciated on the backup unit since it is no longer in control. This allows repairs to be made to the backup unit while the new syscon continues to operate the turbine. The failed unit is not available to become syscon because it has a failed actuator circuit. Once the circuit is repaired, a reset command will clear the fault and restore system level redundancy. Next, let's demonstrate a transfer due to an analog input failure on the syscon unit. Here the unit is in control with a remote speed set point on analog input channel 1. The fault will come in on the syscon and initiate a syscon transfer, putting the fault onto the backup unit. The new syscon keeps control with the remote speed set point from the analog input on the healthy circuit. The failed unit is available to become the syscon because in this case a failed analog input will not result in a system trip. Therefore, it is available to become syscon if a critical error occurs, and it will take control of the system but with limited functionality due to the failed analog input. This concludes the video demonstration of the 505XT dual redundant. For more information, please refer to the manuals shown on the screen. The 505DR supplementary manual has been added as a Volume 3 to the 505XT manual 35018. Thank you.